Hello, my name is Charles Lake. I'm from the Indiana University of Pennsylvania, and I'm happy to be able to contribute to a celebration of Robert Von Dreele's 80th birthday. I'm here to talk about a rare mineral called Mcgovernite. It's got a very interesting chemical formula and some very interesting crystallography. It was discovered in 1927 in a Sterling Hill mine in New Jersey, and it was named after a mine employee, J.J. McGovern, who saved many rare mineral samples from destruction. This crystal structure has remained elusive for 91 years until it was finally solved by a Canadian crystallographer, Frank Hawthorne, in 2018. He was able to solve it in the centrosymmetric space group R3-C and describe the structure as having multiple sites of crystallographic disorder that were difficult to untangle. He provided multiple possible rational explanations for this disorder. His work was supported by previous work when investigators determined that the Mcgovernite had negative piezoelectric effects, which indicate probably centrosymmetric. Now, I was able to get a sample, and I picked off the crystals from the matrix. I ground them up in a mortar and pestle, put them in a Kapton tube, took them to the 11 BM on the APS, and tried to collect some synchrotron data. And whoa, did these crystals like to be in the X-ray beam. They gave a very high resolution data set. You can see it's very clean. We don't see any contaminants in it. Absolutely wonderful data set. We then used GSAS-II, and we indexed the first 26 peaks without any problems whatsoever. The first peak turned out to be the 006 set of planes. And we then used the poly extraction routine to pull out the intensities, to put it into charge flipping. And we let the charge flipping routine go, and we got nothing. Okay, well, it's a complicated crystal structure. Thought it's probably going to give us some trouble. So then what we did is we extracted the data again, but assuming we're non-centrosymmetric. We took those data, put them in the charge flipping routine, we let it go, and we're amazed. After 3,494 cycles, it converged with an R of 7.75%. It solved this huge crystal structure. We looked at the electron density map, and we found that all the cationic sites that were fully occupied were located, and almost all the oxygens, except for about 5 or 6 of them, were located. This was done with powder diffraction data. A couple decades ago, impossible. Couldn't be done. Now, what's going on here is it's not in the charge flipping routine that we had the trouble with the center symmetry versus non-center symmetry. Because charge flipping just assumes P1. It doesn't care. It's with the extraction. When we used the poly extraction and pulled out the center symmetric structure intensities, it didn't solve correctly. When we did the non-center symmetric, it solved correctly. Now, there is the crystal structure that we determined. That's the whole unit cell. It consists of 6 asymmetric units. The unit cell itself is 8.89 angstroms by 203.546 angstroms. And in each asymmetric unit, there are 75 unique atomic sites. We put this into Rietveld analysis, refining, to refine it down. It converged with an R, a weighted R of 5.952%. Now realize, we solved the crystal structure from powder diffraction data, but it is from powder diffraction data. And what does that mean? All our atoms had to be isotropic. We didn't have enough data to actually model anisotropic displacement parameters. The oxygen atoms, we had to constrain altogether displacement parameters. In the silicon, we had to constrain them all together. And that's probably because we had the pseudo-symmetry was causing us problems, gave us a lot of correlation, and we couldn't refine them adequately. And we also had to refine some other properties that you don't in single crystal, like preferred orientation. We then decided to take the single crystal data collected by Hawthorne and download it, load it into GSAS, and look at how his single crystal model would be compared to a single crystal model with our non-centrosymmetric structure. Hawthorne's model converged at 6.817%. where our non-centrosymmetric model converged at 5.624%. We obviously have much better statistics with our non-centrosymmetric model. So what's going on here? Well, what's the differences between these two models? It's because Mcgovernite demonstrates merohedry. That means the crystal structure point group is a subgroup of the lattice, or in our case, the crystal structure appears to have a center of symmetry, but in reality it doesn't. And that's because we're dealing with merohedral twins. In our case, pseudo-merohedral inverse twins. Why is it the pseudo-merohedral twin? Because of our 75 unique atoms, 4 of them violate the center of symmetry. 4 of them do not have inverse equivalence. The other 71 do. Now, our model then, I think, reveals a better crystal structure because we don't need disorder to describe what we're seeing. The pseudo-symmetry is broken by 4 atoms. Therefore, 92.2% of all the atoms collected had a pseudo-inverse pair related by the inversion center at 0, 0, 0.5. These 4 atoms were magnesium 34 and oxygen 75. They had no pseudo-inverse counterparts and an occupancy of 22.7%. And the rest of the time was a arsenic 3 ion, which had a trigonal, a planar arrangement, and a lone pair at the apex. So 25.7% of the time, we had a magnesia octahedra. 77.3% of the time, we had the arsenic 3 trigonal planar pyramid. We could only have one or the other. They're too close together. So are they disordered? No. They're related by the twin. So our structure doesn't have the disordered issue that Hawthorne's did. We could describe it as just a crystal structure with no disorder. In conclusion, this project would not have been possible without the crystallographic skill and programmability of Robert Von Dreele. His work has brought powder diffraction of age. It can now handle and solve large, complicated crystal structures, something that was not possible a couple decades ago. In fact, powder diffraction now can provide insight that allows us to address some problems that single crystal crystallography still has difficulties with. So was Hawthorne wrong? Well, not really. With the data he collected, his single crystal data, there was very little indication that there was merohedral twinning. So solving it in a centrosymmetric crystal structure, well, almost everybody would have done that. And it adequately modeled the majority of the crystal structure. We had the advantage with our powder diffraction data because powder diffraction doesn't really see twinning very well. Therefore, it led directly to the non-centrosymmetric model. So it gave us more insight. And from that insight, we were able to make a better model that described the crystal structure better than Hawthorne's model. Now, remember, these are still models. They're not reality. So our model is better than his model. Does not make his model bad. It just makes ours better. And finally, I want to say that Robert Von Dreele is clearly a selfless individual. He likes helping other people. He writes GSAS-II as a hobby, and he provides it freely to anyone that wants to use it. This is software that rivals much of the proprietary software out there. Bob is clearly a rock star of the diffraction community. I know, Bob, you didn't want me to say that. But Robert Von Dreele's contributions to the diffraction community will continue for generations to come. Finally, I'd like to acknowledge where our sample of Mcgovernite came from. It was donated to us by Dick Hawk, president of the Sterling Hill Mining Museum, and it was transferred to IUP through Richard Bostwick and my good friend Lori Hatherley from ZS Pharma Incorporated. And in conclusion, I want to say happy birthday, Bob. May you have many more. Thank you for working with me. Goodbye.